exchange. All right, so this section is talking about computing the value of trigonometric functions of acute angles. So we're working specifically with acute angles. What are acute angles? Less than 90, very specifically between 0 and 90, right? And there are two sets of triangles in particular, or two sets of angles in particular, that we see used a lot in trig. One of those sets of angles occurs with a 45-45-90 triangle. So I want to start with that kind of a triangle. So consider a right triangle. Which means it's got a 90-degree angle with a 45-degree angle. Now, the first thing that you should remember from geometry ages ago, whenever you took it, or even from early, like in elementary schools where you first encounter it, is that if I've got a triangle here, what do the angles of the triangle add up to?
180.
They add up to 180. So I already have one 90-degree angle, which means the last two angles also have to add up to 90, and one of them is 45. So what is the missing angle?
45.
It's 45. Okay, so this triangle also could be called isosceles because it has two angles that match, right? Two angles matching or two sides matching, and I have an isosceles triangle. Okay, so if I've got this, the first thing then is the last angle is also 45 degrees. So that's my first observation. Second observation is that if I have angles that are the same measure, then the sides opposite them are the same measure. Right? That's what I was just talking about, the isosceles sort of condition there. So the sides opposite the equal angles, in this case 45-degree angles, but this is a principle that's true in general. So the sides opposite the equal angles are equal. And then the third thing is I can actually find the third side in relation to them. That third side is the hypotenuse in this case. So let's take a look and say that we have side lengths that are 1. So we're going to let those each be 1. So how do I find the hypotenuse? Yep. So I'd have 1 squared plus 1 squared equals c squared. So c squared is equal to 2, and c would be. And this is how we develop and how we establish a fact that you may remember. You may remember the ratio relationship between the sides of a 45-45-90 triangle. They're 1, 1, square root of 2, right? And that doesn't mean that they all have side lengths 1 and square root of 2. It just means that that ratio holds. So if I have a side length 5, it would be 5, 5, and 5 square roots of 2. All right? That relationship or that ratio is holding all the time. So you can also take a look, so this is square root of 2, at making this hypotenuse of length 1. And we'll talk later about why that would be helpful to do, but just for the moment, bear with me while I say that I can do it. I have 1, 1 square root of 2. And I could divide each of these by square root of 2. Why do I square root of 2? Because it will turn the hypotenuse, which was of length square root of 2, into the number 1. And if I rationalize the first sets, this would be square root 2 over 2 and square root 2 over 2. And you're going to see us use these later, so that's just why I want you to be aware that they're there. So if I turn the hypotenuse into length 1, then correspondingly the other sides would be divided by square root of 2 and rationalized. So this is a 45-45-90 triangle. There's also 30-60-90 triangles. That's the other common triangle that you've seen talked about before. But you should hopefully be looking at my picture and say, that's not a 30-60-90 triangle. Not even remotely, right? But this actually is an equilateral triangle, okay? So if I have an equilateral triangle, it means all the angles are the same measure, which means all these angles are what?
60.
60, All right, so the first thing I'm going to do is I'm going to put them all in a 60. That is not a good 60. The next thing I'm going to do is I'm going to take this 60, 60, 60 triangle, and I'm going to divide it in half. So the first thing we did is we considered you could say equilateral, you can say equiangular if you prefer. They are the same. So in the equilateral triangle, actually let me get there in a minute. I said that we were going to split this triangle in half, and we are. So we're going to cut this in half. Come on. When I cut this in half, it cuts the top angle in half. So the top angle cut in half will turn the angle into how much? 30. So I'm only going to draw now 1/2 of this picture, okay? The top angle has turned into 30. The bottom angle on the left is still 60. And even if you didn't know that for sure it was the case before, if you add these together and subtract from 180, that bottom angle becomes what? 90, right? So it really is a 90. I didn't just hopefully make that up. They have to add up to 180, and they do now, okay? So we're considering the equilateral triangle, and then cut one angle in half. Let's go back up to that equilateral triangle, and what I'd like to do is I'd like to make all the side lengths 2. The reason I'd like to make the side lengths 2 because the bottom of this triangle, I just cut it in half, right? So if I cut it in half, what is the length of the bottom of my new right triangle?
1.
It's 1. So now I have two sides of a triangle. I have a 1 and I have a 2, and I can find the third side, right? Sure. And you guys all know how to do that, so we're not going to bear too much time on this. This is 1 squared plus, we'll call it b. b squared equals 2 squared. So I have 1 plus b squared equals 4. B squared equals 3. So b is radical 3. All right, so this is another popular or perhaps familiar triangle to you. It has the ratios 1, 2, or 1 square root of 3, 2. That's usually how you remember it. The 1 is opposite the 30-degree angle because it is the smallest side, smallest angle. The 60 degrees has the opposite is square root of 3. That's the next biggest side angle pair. And the last side angle pair is the 90 degrees and the side length of 2. Now, we're going to do the same thing I just did again, and I promise we're going to explain why we're doing this in a little while. But if I took those side lengths, 1, square root of 3, and 2, and I turned the 2, because it's the hypotenuse, into a length of 1, so my hypotenuse, for some reason, I want them all to have length 1, I would divide everything by 2, and you'd have the relationship 1/2, square root 3 over 2, and 1. Okay? And again, that's opposite the 30-degree angle, the 60-degree angle, and the 90-degree angle. That's not 98. Okay, so we're into an example now, and we actually have this problem, sine of 2 theta, and we're told that the theta is 30 degrees. So the first thing we're going to do is we're going to rewrite this as sine of what? Sine of 60 degrees. The next thing we're going to think of is we're going to think of, yes?
Sine of 60.
Because it says 2 theta and theta is 30.
Oh.
Are you with me? Okay, great. So we have sine of 60 degrees. So we're going to think back to that triangle that we had. Okay? That triangle over here for a 30, 60, 90 triangle down here in the bottom left-hand corner, if I take my 60-degree angle and I think about SOHCAHTOA, sine is the opposite, which is square root of 3, over the hypotenuse, which is 2. Very good? So we can use this triangle, and we end up getting that the sine value is square root of 3, because this is the opposite side from that triangle, over the hypotenuse, which is 2. Have you seen square root of 3 over 2 recently? Yeah. Take a look over here. It's right there. That's that value. Let's just keep going. All right, we've got 45 degrees here and 30 degrees here, and it says find the exact value of the expression. Do not use the calculator, of course. The problem with using a calculator is it won't, by and large they won't anyway, give you an exact answer. For instance, this particular problem is going to have some square roots in it when you're done. Your calculator, what does it do with square roots? It puts them in decimal form, and that's not exact. It's great approximation, it's a wonderful tool, but it doesn't do what the directions actually want you to do, which is keep things in radical form. So take a look at this. This says sine of 45 degrees. All right, so let's look at that 45-degree triangle we had way back over here. I can take either 45-degree angle because they match. And if I take this 45-degree angle and I do the opposite, I'll get the number 1. Over the hypotenuse, I have over square root 2. And then if I rationalize that, I get square root 2 over 2. Okay? So this is square root 2 over 2 for the sine value. And again, that should look familiar. That number came up, didn't it? When I turned my hypotenuse into length 1, which seemed like sort of an odd thing to do. All right. Our other one here is cosine of 30 degrees. So 30-degree angle. All right, so here's my 30-degree angle. Cosine is actually adjacent over hypotenuse. So this is the adjacent, square root 3, over the hypotenuse, which is 2. And again, that's square root 3 over 2. We've talked about him already. Oops. Is right here. Now we're done with really all the trig in the problem. At this point, what you're doing is algebra. You're going to simplify these expressions. So what happens when you multiply 2 times the square root 2 over 2? Does it simplify?
Yes.
Sure.
2 over 2. Wait, no.
It is square root of 2. Can I do it without doing the actual multiplication? Those reduce, right? The one on the outside says multiply by 2. The one in the denominator says divide by 2. Well, what happens when you multiply and divide by 2? You cancel out. They didn't really do anything, right? So I'm left with the square root of 2 on top. Can I do the same sort of thing with the 4 and the 2?
Yeah.
Sure. So this 2 will cancel out, reduce, with this 4, but the 4 will become a 2. So I end up here with 2 square roots of 3. And there is no way to combine the square root of 2 and the square root of 3. Those are not they're not common. You know, they're not common values. If I had both been square root of 3, we could have combined them, but we can't here. Now, that works all well and good. You can verify this with your calculator, though. Let me just make that comment real quick. If you take your calculator and you put the original expression 2 sine 45 degrees plus 4 cosine 30 degrees in your calculator, in degree mode, make sure you're in the right mode, and you press enter, and then you put square root 2 plus 2 square root of 3 in your calculator, and you press enter, you should get the same decimal representation. So you can check this with your calculator. You just can't get the answer and then push it back into the radical form with your calculator. Do you see the difference? Okay. We have one more that we're going to do. Grab your calculators out. Because this one says use your calculator, which means it wants you to. And in particular, why do you think it wants you to use your calculator on these? One of them's in radians, right? Which one's in radians here?
4.
The 4 one. What else? You got it. In fact, neither of them are. Neither of these angles are the 30, 60, 90, or 45 angles that we just did triangles for, right? They're not the standard ones that we see all the time used, all right? So you might also real quickly find out that you don't have a button in your calculator that says secant. So how are you going to do that? You bet. We're going to do 1 over the cosine of 41 degrees. Make sure your calculator is in degrees. Now it matters. So, and it says rounded to 2 decimals. So if I round to 2 decimals, what is 1 over the cosine of 41 degrees?
1.33.
It is 1.33. If your calculator is giving you anything different, just see me after class and we'll make sure that everything's going okay with your calculator, okay? But that is the correct solution. Now the second one, how do I know that's in radians?
It doesn't have anything.
It doesn't have a degree marker, right? That's the default. If you don't see a degree marker, it's radians. So take your calculator, make sure you're in radian mode. Again, if you're not sure how to do that, talk to me after class. But you can just enter this one straight in then. I don't need to do any reciprocals, 1 over anything, because I've got a sine button. So you can type sine, you put the number 4, and if you do it correct to 2 decimals, what do you get?
-2.7.
And that's perfectly fine to get a negative. I don't want you to be afraid of negatives, they occur as well. We just haven't seen them with our other triangles so far. So this one's negative, and then the decimal is 76 hundredths. We'll stop here for today.